All right, so let's continue what we were talking about in the previous video. So what I'm going to do is I'm going to take this number here, and I'm going to take this function, and I'm going to go ahead and I'm going to take the first derivative of it. The first thing you do is you take the derivative. You can find the x-intercepts, but that's going to be what we're going to do in the next section. So when we take the derivative, notice this is a product to functions. So this will be capital F, and then this will be capital G. And so the derivative will be f prime g plus fg prime. So when I take the derivative, it will be 4x cubed times x minus 1 quantity cubed plus x to the fourth times 3 times x minus 1 quantity squared. So let me clean this up. All right, so here we go. So what I did basically was I took out the common factors x minus 1 squared, and then I took out x cubed. Those are here and here. And then what was left over, I put here, and then I simplified it all up. All right, so here we are. So I'm going to take the first derivative, and I'm going to set it to 0, and that'll give me like critical numbers. So I have x cubed equals 0. I have x minus 1 quantity squared equals 0, and then I have 7x minus 4 equals 0. So we get x equals 0, x equals 1, and then x equals 4/7. So those are the critical numbers. All right, so now what I want to do is I can do the sign chart. Do the sign chart for f prime. F prime, so we got, now if you notice the x cubed, let's look at the degrees of these. This one's degree, this one's an odd degree, this one's an even degree, and then the last one is an odd degree. This one here is an odd degree because that's a degree 1. If it's even degree, it will not change sign around the root here. So these are the roots of the derivative, right? These are the roots of the derivative. So we set it the derivative to 0. So these are the roots of the derivative. So around 1, it's not going to change sign, but it will change sign around 0 and 4/7. So all I need to do is find the test point for one interval, like -1 here, and then I can use what this odd, even, and odd business tells me. I'll show you. So if I want to plug in -1 into the derivative. So I have f prime of -1 is -1. I'm looking at this times -1 squared, -2 squared, sorry. And then I'm looking at this one actually. And then -1 will give me a -11 inside here. So this is going to give me positive 11. So it's going to be positive here around 0. That's where it was odd. So this is negative 4/7. It's positive. And then after 1, it is going to be positive again. So this is where the derivative is 0, right here. Since I got this test point 0, since this came from this here where the degree was even, the degree was odd, the sign will change from here to here. 4/7, so I got 4/7 from this one here, and the degree was odd, so I know it's going to change sign from here to here. And then 1 came from this piece here, and that's where the factor was even. The degree was even, so I know it's going to change sign from here to here. It's not going to change sign, actually, if it's even. Anyway, plug in test points if you want. 3/7 would be here, 5/7 would be here, and 2 would be here. But it's kind of painful to plug those numbers into the derivative. All right, so now apparently we have, let's see, the first derivative is positive, negative, positive, positive. So it's increasing. So f of x itself is increasing from -infinity to 0, and then it's not technically increasing at 1 because the derivative is 0 there. I think it's going to be an inflection point there. Alrighty. So the first derivative is not going to show us inflection points. So let me write down the derivative again. So f prime of x is x cubed times x minus 1 squared times 7x minus 4. Now I want to take the derivative of this to find the second derivative. So what I'm going to do is I'm going to take this x cubed and I'm going to multiply it through in here because I want to take the derivative here and I'm going to have to, I want to use a product rule and I have three products. I just want to use two products. So let me write that out. So here it is. So now when I take the second derivative, I get 2 times x minus 1 times, I'm going to carry this over, 7x to the fourth minus 4x cubed, and then plus the derivative of the second one. So what I just did was, let me label these again. This one's capital F, that capital F here, and capital G there. So this piece is F prime, this piece is G, and now I'll do F and then G prime here. So we get 12x squared, like that. It's a 28. There we go. All right, so now let me clean this up. All right, so what I did was I cleaned this up, and this is what I got. I had to, what I did was I took out an x minus 1 here and an x minus 1 here, and that goes here. What I could have done is taken out an x squared as well from here and here, but I didn't think about it, and I went ahead and multiplied all this mess in, got all of this here, and then I combined terms and I saw, oh wow, there's an 6x squared in all this. So I took it out and that went here, all right? Okay, so now let's analyze what's going on here. Okay, so at this point, what you could do is you could take the second derivative and set it equal to 0. So you could take all this and set it to 0 to find what are called the inflection points, and then determine the intervals of concavity. But we don't need to do that because the problem isn't asking us that. What I want to do with the second derivative test is find out what's going on with these critical numbers. So we got 0, 4 sevenths, and 1. So let's see what happens when we plug those in. And so we got 0 and 4 sevenths and 1. So I'm going to plug all those into this right here. Okay, so I did that. And the problem is the second derivative test fails whenever you get 0. So it doesn't tell you anything about the first two critical numbers that I put there. But if you look down here, it shows that f double prime of 4 sevenths double prime is greater than 0. And so that's where the graph is concave up. And so since it's concave up there, there's a local minimum there. So the second derivative test tells you there's a minimum there. Did we know that before though? Well, let's just look over here. So it didn't tell us anything about 0 or 1. Let me take off some of these things so that it makes it a little more clear. Okay, I've taken off some of the distracting stuff, and let's see what's going on here. So at 0, the graph, this is the first derivative, the graph is positive, and then it's negative. I'm looking at slopes. And then around 0, it's horizontal, and then at 4 sevenths, it's horizontal, and then at 1, it's horizontal, then it's positive, and then it's positive again. So it's horizontal here. So what happens is the graph will look like this. Kind of like that. Goes up, and then down, and then up, and then it evens out at 1, and then it goes back up again. So what happens is there's a max here, there's a min here, and then there's an inflection point at 1. So the inflection point actually is right here at 1. So notice it goes from concave down here to concave up here, and at 1, let me put the 1 there. It's right here, it's concave up. It's doing this, it's going like this. That's 1 there. So notice that when we did the first derivative test, it was positive and positive. So it's not a max or a min there. If the second derivative gives you a number which yields 0, like right here, there's a good chance that that's going to be an inflection point. All right, so the bottom line is the first derivative told us more about the graph than the second derivative did. But the second derivative did tell us that at 1 there was an inflection point. Okay. Well, it indicated there was 1 because the second derivative is 0 at 1. But the second derivative test told us that 4/7 is a local minimum. Okay, so all of these problems here, these are all really good problems to do. The directions are up here. The one I want to do for you is this one right here. So let's write it out. H of x is 5x cubed minus 3x to the 5th. This will hopefully help us get all this stuff down. The more of these you do, the better. So I'm taking the derivative right now. The fourth, and now let's go ahead and take the second derivative. Well, no, let's not take the second derivative. Let's just set it to 0. So we set it to 0, take a 15x squared out, and we get, looks like 1 minus x squared out of that. And we get 15x squared times 1 minus x times 1 plus x. So our criticals are 0, 1, and -1. So notice that around the 0, 1 has an even degree to it. So our sign chart is going to be affected by that. So here we go. We go -1, and then 0, and then 1. So this is the F prime sign chart. So all these up here are going to be the sign, positive or negative, of the first derivative. So you can plug in test points if you want. I'm going to plug in a 2. So plug in 2 into the first derivative here. Okay. So when you plug in 2, you get a positive here. You get a negative there on the second one, and then you get a positive on the last one. So it's going to be negative there. All right. Now the sign will change around odd degrees. These two have an odd degree to them. So the sign will change around 1. So it's going to be positive here. But it doesn't change around even degrees. There's a 2 there. So it goes from positive to positive, and then it changes around -1. So it goes negative there. So what happens is so we have intervals of increase here, of decrease, sorry, decrease down here, decrease, increase, increase, and decrease. All right, so now let's take the second derivative. All right, so now h double prime of x equals 30x minus 60x to the third power. Okay, so I'm going to set that to 0. So set that to 0, and I'm going to take out a 30x, and I get 1 minus 2x squared. Is that right? Yeah, that's right. Okay, so this is equal to 0, and so this happens at x equals 0, and x equals, when we take this and set it to 0, we get 1 equals 2x squared, 1/2 equals x squared. This would be at x equals plus or minus √2/2, or 1/√2. So this is about plus or minus 0.71. Remember in trig, you had sine and cosine at 45 degrees was √2/2, and that was 0.7071. So it's about 0.71. That's all right. Okay, so what do we do with this? Well, now we find out where so these are inflection points. So let's see, 0 is an inflection point, and √2/2, positive and negative, those are both inflection points. So now I want to go ahead and graph this. Well, I'll tell you what, we probably should just double check that these are inflection points and determine what the intervals of concavity are. So what I'm going to do is I'm going to make a sign chart for the second derivative. So we do that, and that's f double prime. And I've got negative root 2 over 2, and I've got 0, and I've got root 2 over 2. Now, if you notice, 0 was a critical number before. That doesn't mean that it's a max or min. It could be an inflection point. So once again, I'm going to pick a test point. So I'll pick, you can pick test points. You can pick like 1 over here. Since this here is 0.71, you can pick 1 and you can pick -1. Now you can pick test points in these intervals here, but once again, you can use the odd and even properties of the zeros of the second derivative to determine that the sign will change every time. So the second derivative was 0 here, 0 here, and 0 here. When you plug 1 into the second derivative right here, you get a negative answer. So it's going to be negative and then positive, negative and positive. So the graph is concave up, then it is concave down, then it is concave up, and then it is concave down here. Concave down here. So what you need to do now that we have the inflection points and the max and mins, is you need to plug those numbers into the original and see what values you get and then graph it. So I'm going to do that real quick. All right, so here we are. So this is the original function here. And then I plugged in -1, and I plugged in 1, and I got -1, 2, and I got 1, 2 right there. All right, and then plugged in all 3 inflection points, IP meaning the inflection point, and I got these numbers here for them. And then when you plot all of these points here, you get the graph like right here. So let's analyze this for a second. So at -1, 2, -1, -2, -1, -1, -2, it's down there. And at 1, 2, that's right there. I'm on this graph right here. And then at -0.71, -1.2, there's an inflection point there, which means that it's going from concave up to concave down right there. It's real subtle, but it is. So this is the inflection point. That's one of the inflection points. The other one is like right around here. It's concave up and then concave down there. Notice that the 0.00, it's a critical number because the slope is 0 there, but it changes concavity, goes from down to up. So a critical number, which is where the first derivative is 0, can be an inflection point. You got to look out for that. All right, and then you can find the x-intercepts by just taking the original function and setting it to 0. And then this is just strict algebra here. And then I did this on a calculator. Root 5 over 3, I mean, you can kind of tell it's 1.29 because root 5 over 3 is just a little less than root 6 over 3, which is root 2, and you know that is 1.4. So it might be 1.3, something like that. All right, and so there you have it.